Today I am going to talk about power distribution and why we use alternating current and 3 phases and very high voltages to deliver power over long distances. So let's start with a scenario where we want to deliver power to the city of Los Angeles. And we want to deliver that power from Hoover Dam, which is about 400 kilometers away. And we want to deliver 1 megawatt. And that's not enough to power the whole city of Los Angeles, but it's a nice round number to work with, so we'll stick with it. And I want to deliver that at a reasonably safe 100 volts. So how much current am I going to have to deliver from Hoover Dam to give me 1 megawatt at 100 volts? Well, your power is your current times your voltage. So I divide my voltage into my power will give me my current, which is going to be 10,000 amps of current. So I'm going to have to deliver 10,000 amps to Los Angeles to get 1 megawatt at 100 volts. That's a lot of current, but it's doable. Let's go on. So how big of a wire am I going to need to carry 10,000 amps? Well, the current carrying capacity of a wire is called its ampacity, and that is the amount of current a wire can carry without getting hotter than we want it to get. And a copper wire to be able to carry 10,000 amps is going to have to be about 70 millimeters. That might be a little large, but about 70 millimeters in diameter. And if we stretch that 70 millimeter wire for our 400 kilometers between Los Angeles and Hoover Dam, it's going to have a resistance of 0.1 ohms. So now we're getting down to some useful numbers here, so let's move on. So how much voltage am I going to lose taking 10,000 amps across 0.1 ohms? To find our voltage, we multiply. So we take our 0.01 ohms times 10,000 amps, and that is going to take a total of 1,000 volts. So the voltage drop between Hoover Dam and Los Angeles is 1,000 volts. And we need 100 volts left over, so that means I need to start out with 1,100 volts at Hoover Dam to get my 100 volts left over. Now that's not too bad, and I'm going to be delivering 10,000 amps. So 1,100 volts, 10,000 amps, goes 400 kilometers to Los Angeles. I have 100 volts and 1 megawatt left over. So how much power am I losing here? How much am I heating up the desert air with power lost across this line? Well, let's see what it is. We have 10,000 amps and 1,000 volts. Well, to get our power, we multiply those together. So we find out that our power lost between Hoover Dam and Los Angeles is going to be 10 megawatts. So to get 1 megawatt at 100 volts from Hoover Dam to Los Angeles, I have to start out with 1,100 volts and I have to deliver 11 megawatts. I think that that is probably not sustainable. So how can we make this more efficient? Well, let's start by erasing these numbers and getting some new ones. The only one that's going to remain the same is the 0.1 ohms because that's going to be the resistance of that 70 millimeter wire stretched from Hoover Dam to Los Angeles. Now let's start out with 500 kilovolts. A much higher voltage now. So to deliver 1 megawatt to Los Angeles at 500 kilovolts, how much current is that going to take? That's only going to take 2 amps of current to deliver that 1 megawatt from Hoover Dam to Los Angeles. 2 amps, and the voltage drop from Hoover Dam to Los Angeles is going to be only 200 millivolts. So the voltage drop is almost insignificant. And how much power are we going to dissipate? Well, 2 amps times 200 millivolts is going to give us 400 milliwatts. So by kicking that up to 500 kilovolts, 500,000 volts, we have reduced the amount of current we have to deliver from 10,000 amps to 2 amps, the voltage loss from 1,000 volts to 200 millivolts, and the power dissipation from 10 megawatts to just 400 milliwatts. And in fact now, since we're carrying so much less current, we can take that 70 millimeter wire and reduce its size. let's just cut the diameter in half and make that 35 millimeters. So we're actually cutting the bulk of the wire by 3/4. And doing that, we're still only going to use 1 watt, delivering that power all the way to Los Angeles. And in fact, we reduce our losses so much that we can, instead of using very expensive and rare copper, we can use steel reinforced aluminum to deliver our power and save a lot of money in the process. So that explains why we want to deliver our power at these extremely high voltages, because it's so efficient to deliver the power over long distances at those voltages. So why do we use alternating current? That is because we still want to end up with a fairly low voltage at the end. Once again, I'll just say 100 volts. The standard here in America is usually around 120 volts. In other parts of the world, 240 volts. But let's just stick with this number. I want to have that at a fairly low voltage. Well, how do I get my 500 kilovolts down to 100 volts? There are ways to do it without a transformer, but they're not very efficient energy-wise. The most efficient way to change my voltage is through a transformer. Now, for those of you who don't understand transformers, I'll give a very quick explanation. I do have a link to my video about transformers in the description below. Transformer is simply 2 coils of wire, and they're usually set on an iron core to increase the efficiency, to concentrate the magnetic fields and make them work better. But the basic idea is that if I put an alternating current in here, so there's my generator, and so I have my current going back and forth, and what I get is a magnetic field around the wire. As the current goes through, I get a magnetic field. When the current stops and reverses direction, that magnetic field disappears, reverses polarity, and then builds again. And when that magnetic field builds and collapses and reverses polarity, it influences the next wire and causes a current to flow in that wire. Okay, now that only works with alternating current, because if I simply put direct current in here, let's do that with a battery, that magnetic field builds and stops. So I get current through there. When the current stops changing, the magnetic field stops changing, and that magnetic field has to be constantly changing to transfer the energy. It's the magnetic field changing across the secondary that causes it to have current. So I can't have a steady magnetic field, which I would get from DC, so I must have alternating current to get that magnetic field to build, collapse, change polarity, build and collapse again, to influence the secondary. What I can do now is have a different number of turns of wire in the 2 coils. Let's say I have many, many more turns over here. What I'm going to get is a step up in voltage. So let's say I've got 10 volts AC over here, and let's say my ratio of turns is 1 to 10. So let's say I have 100 turns here and 1,000 turns there. What do I get? I get 100 volts over here. So my voltage steps up. Now that doesn't come free, because whatever current is being used over here, it's going to take 10 times that much current in the primary. So my voltage goes up, but my current goes down. So I have a higher current here, high current, low voltage. I end up with a high voltage, low current over here. So there is a trade-off, but this is very efficient. I lose maybe 1 to 3% of my energy in the transformer. So it's a very efficient way to change the voltage. So at this end in Los Angeles, I'm going to come down to a transformer, and actually multiple transformers, but I will transform it down to my lower voltage. I'll do it in steps. I'll step it down to maybe 230,000 volts for local distribution, then down to 10,000 volts, then down to 6,000 volts, 4,000, and eventually I get down to the 240 volts that is used in the neighborhoods, and then finally I get my 100 volts off of that. I'll talk about how that works later. But we have that step down there, and I can only do that with alternating current. And of course, at the other end, what I have are generators that generate, if I remember right, something like 600 volts at a fairly high current, and that goes through a step-up transformer. I'm not showing both conductors here, I'm just simplifying at this point. So that goes to a step-up transformer from the generator, and so I step my voltage up to 500 kilovolts, send that across the desert to Los Angeles, and then step back down to where it's needed to eventually get back to 100 volts. So the reason we use AC is because we can use transformers to step it up to a very high voltage and then step it back down to a reasonably low voltage, which we cannot do with direct current. Now, if you look at the power lines going across the desert or other areas where power is distributed over long distances, you will see that the power poles, this is a typical 500 kilovolt power line in the western United States. Can't vouch for any place else. Notice that we have 3 wires. Almost always 3. Why is that? Well, that's because the power is sent in 3 phases. What do I mean by that? What I mean is that the timing of the wave in the different wires is different. Let me show you what I mean. So when we send alternating current, I'm going to draw a line here that represents 0 volts. And so as time goes by, our voltage is going to get higher and lower, change polarity and get lower and higher. So time is horizontal, voltage is vertical. So our voltage goes up, levels off, and then goes back down to 0. In America, what comes out of the wall goes up to about 170 volts approximately, goes back to 0, then goes down to minus 170 volts. In other parts of the world, it's a different voltage. Didn't I say it was 120 volts here? Well, this is the instantaneous voltage. It goes up to 170, back down to 0. But if we take an average, a special kind of average called the root mean square, we find that that 170 volts contains the same amount of energy as DC at 120 volts. So this voltage is going up, down to 0, minus voltage, back to 0. So it's changing all the time, and it has the same amount of energy as 120 volts DC. So we call that our voltage. Formally, it's called the RMS voltage, root mean square, but it does go up to 170. So the voltage goes up, levels off, comes back down to 0, goes down to negative 170, and then back down to 0. And it repeats that 60 times every second in North America, and most of the world it's 50 times every second. So this whole cycle takes 16.66666, repeating decimal, milliseconds, and that would be 60 times every second. So if we are sending our power on this wire, and we'll just go ahead and put in both wires here because we really will need 2 wires, and we'll see how this works out in a moment. So the voltage goes up and the voltage goes down, and it's pretty low voltage and even 0 volts here. Voltage goes down, it can do some work, goes back up to 0 volts. And in this region, it's not doing much work, and of course it's doing no work at 0 volts. So some of the time, we're sending no power at all. So that's one problem we're going to solve with the 3 phases. The other one I'll show you as I show how the phases work. So let's take a look at that. What we have is 3 wires carrying the power, and I'm going to add a 4th wire because we need it, except we don't. I'll just add a 4th wire. I will add that right here. And I'm going to actually take one of these wires and change the color because this is the return wire. And we'll show how that works in a moment. Now, as you know, electricity has to follow a loop. So at any moment in time, the current's going to be going around this way. Another time it's going to be going around the other way, back and forth in alternating current. And so the current travels in this direction and then returns this way. And then the other half of the cycle, it travels out this way and returns that way. Okay, so with 3 phases, what we have is 1 phase. The voltage is going up and down and back up. Here's our 0 volts. And let's say that's this one right here. The next one, though, it's going to be a little bit later in the timing. So that's what the phasing means. It's the timing of the waves. And we'll start it right about here, probably right about there is probably about right. It goes up and down. Same exact voltage, just a later time. And then the 3rd phase, probably right about here, goes up and down and back up. And I'm going to carry these back to their beginnings. So we have the voltages going up and down and up and down. It looks a little cluttered here, but here's one phase going up and down. The next one's going up and down, up and down. Now let's see what happens. So we have some voltage coming out this wire, and it's returning on that wire. And we have another time the voltage is coming up on this wire and then again returning on that wire. Now it's looking like this wire is going to have to be 3 times as big because it carries all 3 phases, right? Well, what's actually happening, if we look more closely, at one moment in time, this wire is carrying current this way and then returning that way. But remember, that voltage goes down and the current goes down with it. So after a while, the current has dropped down and not as much current is traveling this way. And at that time, the next phase is coming to its peak. So it's not peaking at the same time. So even though this wire has to carry the return from this wire and the return from that wire, and I'm going to use the term phase sometimes. In fact, in the industry, they call those 3 wires the phases. So this one peaks and then goes down, and as this voltage is going down, this one's coming up, and so it's not carrying all 3 at the same time. And in fact, by the time this one comes up, this is probably trying to pull it this way. And what actually ends up happening is that the 3 phases together work such that as this one's sending current, and then this one sends current, and then this one sends it back this way, and that way they all come together, that actually none of the current goes through this wire. So it's going through this wire, then returning through that one, and then comes out this wire and returns through that one, then comes out this wire and then returns through that one. Of course, it's not quite so like here's one, there's the other one, but they're going up and down and up and down, and just the timing of these peaks are just perfect so that as this wire is pushing current out, the other wire is sucking current back, and just timed perfectly so that we actually don't even need that 4th wire. So what we're doing is we're carrying as much current as 4 wires in only 3 if we use the 3 phases. Now there is a 4th wire. I'll put it back here, but I'm going to put it as a, well, probably should put the blue marker back in there just to remind us that it's different. And the main thing is that it's a much smaller wire. We need to have a little bit of a return, because if these are not being utilized the same way, if we're taking more power out of this phase than that phase, then there will be an imbalance. And so we need to have that return wire for the little bit of imbalance that we might have. So 3 big wires carrying the current out, and then 1 small return wire, because if everything balances out, we don't even have any current on that return wire. And of course, it's going to be grounded in 1 or more places so that the electrical potential here is 0 volts compared to the earth. So that's going to be connected to ground. And so that's going to be our 0 volts. And so all these voltages here will be referenced to the earth. So the reason we have the 3 phases, if I will declutter this and simplify it a little bit, is we have wire 1, wire 2, and wire 3 hanging from our tower. I won't draw here. And so the power is coming out this wire and returning through this one, and maybe a little through this one, just depends on the timing. They're going to be changing constantly, but they all balance out so that we don't have to have a 4th return wire. So there's our 3 phases. Now the other reason is, as I mentioned, is that with a single phase, there's a lot of time where we are near or at 0 volts. And so if we have a motor that runs on single phase, well, it's not going to be producing any power during these times. So if we have a motor that's designed to work on all 3 phases, then when it's losing power from this phase, it's starting to get power from this phase. When this phase starts to drop down, it starts to get power from this phase. And so these all work together so that the power in the motor is evenly distributed across the 3 phases, and it doesn't have any time that it's not actually producing power. So industrial motors will be 3-phase motors, and so they will send all 3 of those phases to industrial areas to deliver to those 3-phase motors. Now when they deliver those 3 phases to a industrial area, there's the 3 phases and the ground, they'll step that voltage down so that the voltage between any one of these phases and our neutral wire, which of course once again is grounded somewhere to reference everything to ground, that's going to be 120 volts. So between this phase and ground, 120, that phase and ground, 120, that phase and ground, 120. But if you go between any 2 of the phases, we find that there's 208 volts between the phases. Why isn't it Why isn't 240 volts between the phases? Well, because of course the voltages are happening at different times, and it works out so that the averaging of the voltage between any two of them is 208 volts. So to get 120 volts, we take any phase and the neutral, we get 120 volts, but we need 208 volts to run industrial motors. But to get the 208 volts, we will work between the phases themselves. And sometimes they will take this into a residential neighborhood, and they will take the neutral. And so your circuit breakers, let me draw the breaker box sort of here, will have one phase, another phase, and then the neutral in the middle. And we'll have circuit breakers that connect. There's a circuit breaker, but it only connects to the neutral and one phase. What does that give us? 120 volts. It might be a different voltage. Actually, I've seen in the Southern California area, it's more likely to be 117, but it just depends on where you are. 120 volts, and then let's say the next breaker connects to this phase and the neutral, giving you 120 volts. And they will alternate which circuits are on which phase and the neutral, and balance that out. So half of the sockets in a house and half of the light switches will be on one phase and neutral, and the other half would be on the other phase and neutral. So we put some more breakers in here. There's one connected there, put another breaker in here, and that one's connected to there and there. So they're all 120 volts. There's our wires coming out of them. 120, 120. So what do you do if you need an air conditioner or a clothes dryer or some other appliance that needs 240 volts? Well, they'll call it 240, but they simply take a breaker that's designed to go across two phases, and what do we get? 208 volts. Now, I actually lived in a house that was wired like this, and I used to think it was the norm, but apparently the norm is actually to take a single phase into a neighborhood. So here come the three phases into an industrial neighborhood, and they'll take one of those phases and the neutral, send that through a transformer, and come out with a new neutral, and that of course will be grounded somewhere. I'll make this blue because I can. That's going to be grounded somewhere so that it's referenced to ground. There's our neutral wire, and this is going to be a total of 240 volts or 120 volts on each phase. So when we get the single phase, which is the norm in residential wiring, it will be this what they call split phase, where you get 120 to neutral, 120 to neutral, or 240 across both. And once again, that goes into a breaker panel. It might go to the same style of panel. There's another style too where the breakers just look different. The connections are different, but it's the same thing. Some breakers go to one phase and ground, other breakers go to the other phase and ground. And to get the full 240 volts, you have breakers that go between the two phases. So that's the basic idea of how we get that power off to industrial areas and to residential areas. Now, I may not be getting the wiring here exactly 100% right. I'm not trained as an electrician or a power engineer, and exactly how they wire them might be a little more like I described for some areas where you get two of the phases, and exactly how they wire the transformer could be different. Maybe I'll cover that in another video, but the basic idea is that most of your houses are wired with the split phase, 120 to neutral, 120 to neutral, and then 240 across both of the phases, where some are wired with the 208 volt standard I mentioned before, coming directly off the three phase. Another thing worth mentioning at this point is the transformer designs used for the power distribution. One way is called the Y, and so I'm going to draw three coils here in the shape of, guess what, a letter Y. And this is spelled W-Y-E if you see it written out. And of course, this is just a schematic view. They're not laid out physically like this. It's going to be more something like there's one winding, there's another winding, there's the third winding, and that's connected to that and to that. And so there's our three phases and then our neutral. So there's our four wires, and that's more of another schematic way of showing it, but showing that it's not going to be laid out in the shape of a Y, but we draw it that way because it is a convenient way to draw it. And of course they come together in the middle. And an advantage of the Y winding is that we put the 3 phases out here and we get a nice neutral with 0 voltage in the middle. And we can ground that wherever it's appropriate to ground it, and there is our neutral wire. So if we want a neutral wire, we might want to use the Y winding. The other style, which you might be able to guess, is shaped like a triangle, and we call this the delta, with 3 phases here, here, and here. Now, we don't have a convenient place for a neutral. Often they might put a tap in the middle and ground that, making that a neutral wire. Of course, you know, it's not grounded out where it's used. The ground is going to be further away, but that's going to be our neutral. And so you have to tap it to get the neutral, but in lieu of that, there's no other way to give us a neutral wire. But the advantage of the delta winding is that it suppresses the 3rd harmonic. In other words, when we send power around, we might get a flattening of the curve because of distortion. And flattening that sine wave introduces odd harmonics. And the 3rd harmonic is the strongest of the harmonics. It's the first odd harmonic. And the delta winding tends to suppress that 3rd harmonic. And so we might use the delta winding to give us a cleaner sine wave, suppresses that 3rd harmonic, which would be 180 hertz, and gives us a cleaner sine wave. So that's just the style of the windings. And a transformer could have both Y windings, both delta windings, or a Y primary and a delta secondary, or a delta primary and a Y secondary. However, the engineers need to design it for their particular purpose. And another thing I need to mention here, of course, is I've been talking about the neutral wire and that the neutral wire is grounded, but that is not your ground wire. We have to have a separate ground wire for safety. The neutral wire is going to go some distance from where it's grounded. And it may be grounded in multiple places, but here it's coming off of, let's say it's coming off of our Y transformer or wherever it's coming from, and we have currents over here. Here's our load, so we have current going this way and that way, and it's fairly short and it should not have very much voltage on it. This should be 0 volts. However, if we are carrying a significant amount of current, this is going to become something greater than 0 volts. So what we need is a separate ground wire. And as often as not, in fact more often, that's going to be grounded somewhere near the outlet so that we have a good 0 volt reference hooked up to ground for safety purposes, especially for faults, because this could be miswired or could get high voltages on it, and we want a good solid ground for safety purposes. So we don't want to use the neutral for our ground because it might not always be 0 volts. So the ground wire would be a separate wire from the neutral. The neutral's carrying current. The ground wire should only carry current when there's a fault. And last but not least, I'm going to talk about the different circuits you might see in the home. Now I'm going to be talking about North America because that's where I am. Things might be different where you are. In fact, the socket design is almost certainly going to be different. In North America, our sockets look pretty much like this. There's a wide blade, a narrower blade, and the 3rd ground socket. This is going to be the neutral, and that's going to be the hot. And this is for a typical 15 amp circuit. So most of our circuits in North America will have a 15 amp fuse somewhere. But sometimes, especially in industrial buildings or commercial buildings, you might see an outlet that looks like that. Did I get the tail the right way? Well, anyway, the neutral is going to have a T shape, and that is for a 20 amp circuit. So if you have a 15 amp appliance, do not plug it into a 20 amp circuit, right? No, of course not. The 15 amp appliance is only going to take a maximum of 15 amps. In fact, most appliances are going to take a lot less than that. But your typical circuit can deliver a maximum of 15 amps. So I can put a 10 amp load, a 5 amp load, a 100 milliamp load, doesn't matter. I can also put a 15 amp appliance in the 20 amp because it doesn't care. But what I don't want to do is take a 20 amp appliance and plug it into a 15 amp socket. I'm going to blow the breaker. So a 20 amp appliance is going to have a plug. We look at the plug end of this. The neutral is, of course, going to be the other side. Here's the hot. There's the ground plug. Of course, if I try to draw this, this is the end with terrible drawing there, but this is the end with the blades on it. blade's going to be sideways so that it will fit into that part of the T, but it will not fit into the 15 amp socket. So if you have a 20 amp appliance, you can only plug it into a 20 amp socket. You cannot plug it into a 15 amp socket. But a 15 amp or lower appliance will have no trouble plugging into a 20 amp socket. Now, another interesting thing, knowing what we know now, is since your 240 or your 208 volt circuit is actually made from your two hot wires connected to your neutral, so hot to neutral is 120, hot to neutral is 120, hot to hot is 240. Is there a way to take a 240 volt outlet? Let's draw one from North America here. If I have a 240 volt outlet, is there a way to split off the two 120 volt sides on there? And yes, there is. You can actually buy harnesses to do this. You can buy, I know that Grainger sells them. I'm sure you can get them in other places. A place where you can plug into your 240 volt circuit and that plug comes off. Let's see if I can draw a crude plug here. Wire comes off the plug. That's in your circuit there. And it will go to two separate, terrible drawing here, but it serves its purpose, 120 volt outlets. And I don't know how often that's done, but I know you can buy that harness to split one 240 volt socket into two 120 volt sockets. And there may be equivalents for other countries that don't have the same standard we do in North America. Now, another thing is, well, what if I need just temporarily 240 volts instead of going and buying a 240 volt breaker? Now, really the right way to do this if you need 240 volts is to get a 240 volt breaker. Once again, the style I've worked with has the two hot rails and the connectors, and they just kind of snap into the rails. There's another style that's probably more common, but the idea is the same. And that will give me my 240 or 208 volts, depending on what kind of circuit I have. That's the right way to do it. But what if I just need to run an air compressor for one day or something? Could I not go to two different sockets in the house? Like I said, half of these will go to one side of the house. So some of your sockets will be wired with this hot and that neutral, and the other half of your sockets will be wired with this hot and that neutral. Could I go find those and combine them together to give me my 240 volts? Theoretically, you could. Well, not only theoretically, I've seen it done. It's non-standard. It's dangerous if you don't do it right. But if you find somebody doing it, running two extension cords from two different places in a house, coming together to one plug and have an air compressor or some other piece of equipment temporarily plugged in there because, hey, it's just a hack to get them going for a day, now you know what they're doing. Now that I've said all I have about alternating current, let's take a look at another scenario. Let's get back to our power distribution. So let's erase almost everything here. Let's go back to our wire going from Hoover Dam to Los Angeles. And there is a slight problem with alternating current. There is cross-coupling between the wires from capacitance and from inductance also. And there's cross-coupling between the wires and ground, and so there's a little bit of loss there. And there's also loss from coronal discharge, which apparently is worse with AC, but I haven't been able to confirm that, but that's what some people have said. But there's a certain amount of loss with AC that we would not have if we used DC. Once we step this up to our 500 kilovolts, why don't we convert it to DC and send it over and then convert it back to AC at this end? Well, it's not cost effective. It's a lot cheaper to build the AC infrastructure than it is the DC, unless you go a certain distance. Somewhere around 500 kilometers, I believe, is where the trade-off point gets to where it's actually cheaper to build a DC system than an AC system. The wiring is cheaper, the towers are cheaper, and you'll see why in a moment, and their losses are less. And so sometimes they will build DC power lines. In fact, here in California, we have two of them. One of them starts up in the Dalles, Oregon. So here's a crude drawing of the state of California. And up in the Dalles, on the Columbia River, is a power plant that sends most or all of its power off through the desert and back down to Sylmar, California. And at the power plant, it is stepped up to 500 kilovolts, converted to DC, and then comes back down to Sylmar, where it goes through an inverter and is converted back to AC for use in Los Angeles. And there's another one in Delta, Utah, just about smack dab in the state of Utah. It starts here at the Intermountain Power Plant near Delta, Utah. This converter plant steps the voltage up to 500 kilovolts and converts it to direct current. The power plant is currently coal-fired. However, Los Angeles is the largest customer, and California has mandated a turn away from coal power. So they plan to convert the power plant to natural gas by 2025. And then that comes down near Las Vegas, works its way down, and eventually ends up in a town called Adelanto in California, where it's converted back to AC and then works its way into Los Angeles. And I don't know about the capacity of the Intermountain DC intertie, as this one's called, but I do know the capacity of the Pacific DC intertie is such that it provides enough energy for the entire city of Los Angeles. Not the whole county, but it provides enough energy for about 3 million people on that one power line. So, although almost always our power is delivered as high voltage AC, occasionally it's delivered as high voltage DC. And as you saw in the short video there, you can recognize these DC power lines because instead of having the 3 wires, they will have 2. So if you're driving between Los Angeles and Las Vegas, you pass north of Victorville, you'll see this cross the freeway. East of Barstow, you'll see it cross again. I think you see it cross again. Let's see. Yeah, just when you get to the California state line, you see it cross again. And then east of Las Vegas, you see it cross again. So here's Interstate 15, and so it crosses here, crosses there, and crosses there. And you see it cross the freeway 4 times, and you can recognize it by the 2 wires rather than the 3 wires. And the one that comes from the Dalles, Oregon, comes roughly down US 395, and you can see it up in the desert in that particular area. In fact, here's a picture of it next to an AC power line that runs along the same right-of-way. So to the right is the AC power line, and to the left is the Pacific DC intertie following the same right-of-way. And the cost of the rectifiers and the inverters needed to convert to DC and back to AC is coming down to the point where you might see these DC lines becoming much more common than they are now. The actual building of the line is cheaper. There's less wires. You don't have to carry 3 wires with the infrastructure to carry 3 wires. And in fact, the DC system sometimes carries even more current because what they'll do is instead of making one of these positive and the other negative, they might make them both positive and use the ground as the negative for the return. So the current flows out this way and comes back on the ground. Another interesting thing that just came to mind is that these do have a grounding system, and sometimes they're miles away from the terminators. For example, the Intermountain DC intertie ends in the desert near Adelanto, and then there's a wire that goes many miles backtracking to a number of buried iron plates that become the ground. And for the Pacific DC intertie that ends in Sylmar, there's a wire that goes out into the Pacific Ocean to a number of steel blocks or iron blocks that make the ground for that system. And so they're well connected to ground, so they can, if they need to, send all the power on the wires and have the return come through the ground. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at Vocademy.net, you can go to patreon.com/join/Vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.